Calculus. I know, for a lot of people, that word alone is enough to make you nervous. But what if I told you it's not just the scary math class, but actually one of the most powerful ideas humans have ever come up with? Today, we're going to pull back the curtain and see what calculus is really all about. It's the secret code for describing a world that just never, ever stands still.
Just think about it for a second. A falling apple, the stock market, the planets zipping through space, right? They're all in constant motion, always in flux. And that presents this huge, fundamental problem. How in the world do you measure something that won't stop changing?
And that question, that's the whole ballgame. The answer is calculus. At its heart, it is the mathematics of change. It's the language we invented to describe and even predict anything that's dynamic. It's less about static numbers and way more about the flow of how things are evolving from one moment to the next.
Now, to really wrap our heads around this, we've got to look at two ancient problems that stumped the greatest minds for centuries. The first one, it's all about speed.
You know, if you're moving at a perfectly constant speed, it's super easy. Your graph is just a nice straight line. The rate of change, or what we call its slope, is the same everywhere. But let's be real. The world isn't like that. We speed up, we slow down. Our motion creates these curves where the steepness is literally changing at every single point. Now that is a problem.
And this leads to a really fascinating puzzle. When you're driving and you glance down at your speedometer, it's not telling you your average speed for the trip. It's telling you your speed right now, at this exact tiny instant. How on earth does it do that? How can it possibly calculate that? This is what mathematicians call the tangent problem. The big challenge is to figure out the slope of a line that just barely kisses the curve at one single point. Because that slope, the steepness at that one exact moment, is the instantaneous rate of change. That's the secret.
Okay, so that's problem number one. Problem two, well, at first, it's going to seem totally different. But just hang with me here because the connection between them is where the real magic happens. Let's talk about the problem of curved areas.
All right, so take a look at this. We've got this shape. The problem looks simple enough, right? Three of the sides are nice and straight, but the top is a curve. So how do you find the exact area of a shape like that? I mean, finding the area of squares and triangles and rectangles, that's ancient stuff. We've known how to do that forever. But the second you throw in one little curvy edge, suddenly all the old rule books go right out the window. So here we are with two huge and seemingly unrelated problems, figuring out instantaneous speed and finding the area under a curve. And then along comes this one single brilliant idea that just blows the doors off both of them. And that idea is the concept of a limit. The idea of a limit is it's pure genius in its simplicity. It's basically asking, what if we can't find the perfect answer directly? What if, instead, we just sneak up on it? What if we just get closer and closer and infinitely closer to the answer? Okay, let's take this idea and apply it to our speed problem. Remember, finding the slope at one point is crazy hard. But finding the slope between 2 points, hey, that's easy. That's just basic algebra. This line connecting 2 points on a curve is called a secant line, and it gives us a pretty good average rate of change. So this secant line gives us a decent estimate for the slope at that first point. It's a rough approximation, it's not perfect, but it's a start. But now, watch this. This is the cool part. As we slide that second point closer and closer to the first one, the secant line starts to pivot, becoming a better and better match for the curve. This is the limit in action. As the distance between the points approaches zero, the slope of our secant line becomes the true slope of the tangent. Boom! We've just found our instantaneous speed. So this whole getting infinitely close thing is pretty powerful, huh? But can it really solve our area problem too? Absolutely! We can't measure that curvy shape directly, but we can fill it with something we do know how to measure. Simple little rectangles. So by calculating the area of each of these rectangles and then just adding them all up, we get an estimate of the total area. Now, it's not a perfect fit. You can see the gaps and the little bits that poke out over the top, but hey, it's a start. And here comes the magic trick all over again. What happens if we use more rectangles, but we make each one way, way thinner? The gaps get smaller, the estimate gets better. So what if we could use an infinite number of infinitely skinny rectangles? Their total area would perfectly match the area under the curve. Once again, this amazing idea of a limit solves the impossible.
So, let's just pause and think about what just happened. We had two completely different problems. One about change in a single instant, the other about total accumulation over time. And both of them were solved by the exact same core idea. This connection isn't some weird coincidence, it is the entire foundation of calculus.
So let's recap the big picture here. The tangent problem, that's what gave us differential calculus, which is the study of derivatives or instantaneous rates of change. And the area problem, that gave us integral calculus, the study of integrals, which is all about summing up infinite pieces. Two major branches of mathematics, born from two ancient puzzles and unlocked by one master key, the limit.
And believe me, this is just the beginning. These core ideas expand way beyond a flat piece of paper. They go into 3 dimensions, allowing us to calculate the flight path of a satellite, the volume of a crazy complex shape, and so much more.
In the end, calculus isn't just a subject in a textbook. It's a lens for seeing a universe that is constantly, beautifully in motion. It was invented to describe the world, and in turn, it gave us the power to actually change it, from building skyscrapers to launching rockets. Which leads to one final, really exciting question. What are we going to build with it next?